Hello all. In this video we are going to explore the notion of electric field lines. Electric field lines due to a point positive charge. Consider a positive point charge Q. This charge is called a surge charge as it produces an electric field around it. Consider another positive point charge Q0. This charge is called test charge as we determine the electric field pattern using it. The charge Q0 experiences repulsive force F bar due to the source charge Q as both are positive charges. The force F bar is along the straight line through the source charge and is directed away from it. We say that the force F bar is directed radially outward from the source charge Q. It is obvious that the forces on the test charge will be directed radially outward at any point on the straight line through the source charge. The direction of an electric field E bar is the same as that of an electric force experienced by a positive test charge. The electric field is directed along this line at every point on it. We call this line an electric field line. The electric field is directed radially outward from a positive point charge all around it. The electric field lines thus originate from a positive point charge and advance radially outward from it. Now consider a negative point charge as a source charge. The positive test charge Q0 will be attracted by a negative source charge. The electric field is thus directed radially towards the negative charge. A straight line directed radially towards the negative charge represents the direction of the electric field everywhere on it. Electric field due to a negative point charge is directed radially towards the charge all around it. Thus, electric field lines due to a negative charge are directed radially towards the charge and terminate on it. So far, we saw electric field lines due to a single point charge. The field lines are straight lines. The electric field lines due to several point charges are, however, curved lines. The electric field lines serve to represent the direction of electric field. To draw field lines, one first draw arrows representing the direction of electric field at as many points as possible. A smooth line is then drawn passing through these points in such a way that the lines advance instantaneously along the direction of the electric field in passing through the points. In other words, arrows representing the direction of electric field are tangential to the field lines. Electric field line is defined as the line such that the electric field at any point on it is directed along the tangent to the line at that point. Suppose that the two field lines, field line 1 and field line 2, intersect each other at point P. The net force experienced per unit charge by a positive test charge, that is an electric field intensity at any point in the electric field, is unique. The field vector at any point P is tangential to the field line at that point. The field vector cannot be tangential to the two lines that intersect or cross each other at the point of intersection. Thus, field line 1 and the field line 2 are not true field lines. That is, the field lines never intersect. Electric field lines due to two positive charges, very close to one of the charges. An electric field line due to a point charge Q1 at a point P close to the charge is radially outward as shown. Being far away from the point P, An electric field due to another positive charge Q2 at point P is much weaker compared to the field E1 bar. The contribution of the field E2 bar to the net field at point P is negligibly small. Hence, the net field E bar at a point P is nearly equal to the radial field E1 bar due to a charge Q1 alone. We conclude that in the electric field produced by two positive point charges, the field vectors and hence the field lines close to the charges are radially outward. Consider two positive point charges as shown. Consider a point A near to one of the charges Q1 than the other charge Q2. The electric field at a point A due to the charge Q1 is E11 and that due to the charge Q2 is E21. These fields are radial. The net electric field E1 bar is obtained by using parallelogram law of vector addition. The electric field line at a point A deviates from the radial path. It deviates away from the midline. This is true for every point on the side of the midline where charge Q1 is present. Similarly, the electric field at a point B deviates away from the midline. For simplicity, we assume that the two charges are equal. We investigate the nature of an electric field at points equidistant from the two charges, that is on the midline as shown. The electric field at a point A due to the charge Q1 is E11 and that due to the charge Q2 is E21. These fields are radial. The resultant electric field is obtained by using parallelogram law of vector addition and is along the midline as shown. Similarly, one obtains net electric field at a point B. It is clear that the electric field everywhere on the midline is directed along the midline. The midline therefore also represents the electric field line. The electric field lines on either side of the midfield line cannot cross the midfield line and must shoot to infinity as they approach the midfield line. From the analysis so far, one can now construct the field pattern of an electric field due to two positive point charges. The field lines originate radially from the positive charges and curve away from the radial path as they advance. The field lines originating from one charge are not extending into the region of other charge. This may be seen as the repulsion between the field lines and may be associated with the fact that like charges repel. The field lines due to unlike charges, that is due to positive and negative charges, can be similarly constructed. The field lines originate from the positive charge and end onto the negative charge. Unlike like charges, the field lines advance from a positive charge to the negative charge, connecting the two charges. This feature may be associated with the attraction between unlike charges. The radial lines due to individual charges can be shown for comparison. The field lines due to a point charge are radial. According to Coulomb's law, the field is stronger near the charge. We also see that the field lines near the charge are closer to each other. The strength of the field decreases as we move away from the charge, and at the same time, the same set of field lines diverge further away from each other. From this observation, we can relate the field strength at a point to the density of field lines at that point. Greater the density, greater is the field intensity. Note that this observation is made for an electric field due to a point charge. The origin of an arbitrary electric field can be traced down to certain distribution of point charges. We can therefore generalize the fact that the field intensity increases with the density of field lines to an arbitrary electric field. An arbitrary electric field means an arbitrary pattern of field lines. The electric field is stronger in the region A, where the field lines are closer to each other. The electric field is weaker in the region B, where the field lines are further apart from each other. The notion of electric field lines was proposed by Faraday in order to understand how particles exert force on each other even without physical contact. It is now understood that the field lines is not just a mental idea, but it also has important physical relevance. Thank you.